Hi everyone, welcome back to another video. So in this video, we're going to be going through waveforms, and we're going to talk a bit about the different types of waveforms that you have, both in terms of their categories and also their actual specific types. I'll give you some examples as well, and then in the next video we'll go more maths heavy. So this video will just be like an introduction, and then in the next video we'll go through some calculations and stuff as well. So first, let's jump into the definition of what a waveform is. All right, so a waveform is a visual representation of the variation of voltage or current over time. So if you think about that, right, imagine you've got a graph here, you've got time, and the waveform is a visual representation of the variation of that voltage or current over time. So if you imagine you've got a voltage going along here, so you've got a steady line of voltage here, let's say this is 12 volts, then here you can see we've got a waveform which represents a steady 12-volt voltage. So if instead you had a waveform that looked like this, then you could see that you had a waveform that started off at 0 and then went up to 12 volts, came back down to 0, went back up to 12, and then went back to 0. So it's a visual representation of the variation of voltage, or can be current as well, over time. Alright, so in terms of the waveform categories, we've got two types of waveforms. We've got unidirectional waveforms, and we've got bidirectional waveforms. Unidirectional waveforms flow in one direction. They can be positive or negative, but they never go across the zero axis point. It stays either above or below. So these two waveforms that I mentioned here, they're both unidirectional waveforms. They don't go below the zero axis, they both stay above it. So with unidirectional waveforms, they never cross the zero axis, and they can be positive or negative. So with bidirectional waveforms, another word for bidirectional is alternating. Hence we have alternating current, AC. Alternating. So alternating or bidirectional waveforms, they constantly cross from a positive direction to a negative direction. So they're alternating constantly from positive to negative, back to positive, back down to negative, constantly crossing the zero axis. So bidirectional, alternating, constantly crossing the zero axis, yeah? All right, let's give you some examples. All right, so here we've got a waveform. This is called a square waveform. And as you can see, it's going in one direction across with time, but it doesn't cross this zero axis here, right? It stays above. So for example, it comes up close to, so this is 12 volts, maybe this might be 10 volts, and this could be 5 volts. So you can see it goes from 5 volts here, up to 10 volts, back down to 5 volts, up to 10 volts, back down to 5 volts, right? But it doesn't cross the zero axis, so this is a unidirectional waveform. So another waveform here we've got, which is unidirectional. This is a sine wave. So it starts at minus 12 volts, goes up to like probably what, minus 5 volts or something like that, and then comes back down, goes back up. But because it doesn't cross this zero axis here, it's still unidirectional. So we've got another square wave here, but it goes along the zero axis. Sorry, my line's not the best, but hopefully you know what I mean. I'm not the best at drawing. But yeah, here, the square wave, it's going up and down, oscillating. So let's say this is 0 volt, this is 1 volt. Then you can see it's oscillating constantly from 0 up to 1. And this is mostly used in like digital electronics and logic circuits, stuff like that. Clock pulses, these kind of things. So clock pulses are actually one of the biggest uses for unidirectional waveforms. Another big use is for DC current. So imagine you have, for example, one of those square batteries, you know, these ones. You got a square battery, it will be a 9-volt battery. So the 9-volt battery's waveform would look like this. It doesn't cross the zero axis, it just gives that a steady supply of 9 volts throughout time, right? That's another example of unidirectional waveforms. All right, so let's move on to bidirectional waveforms. So here I've drawn two waveforms over each other just to show that this is how you might often see some waveforms. You might see them overlapping. So let's say, for example, we'll call the red waveform A. We'll call the B waveform B. The waveform A is a square wave, and waveform B is a triangle wave. So as you can see here is the zero axis. In this instance, we've got current. We've got 5 amps and minus 5 amps. So as you can see here with the red waveform here, it's at about, let's say, 3.5 amps here. It stays at 3.5 amps, drops down way past the zero axis and drops to minus 5 amps. Stays there for a bit, then comes all the way back up to 3.5 amps. Now for the blue wave B, so you can see it starts at 0 amps, comes up here to 5 amps, comes all the way back down to -5 amps down here, comes back up over here to 5 amps, and then comes back down here. So as you can see, both these waveforms, they're constantly crossing the 0 axis, which is what makes them bidirectional. So for example, in this instance, current is going positive up, and then it's coming negative down. So the current is constantly going backwards and forwards, oscillating, hence the term alternating current. Alright, so I've got another 2 waveforms here. So here we've got a sawtooth waveform, which is the green one. We can call that A. And then we've got the red sine wave waveform. We can call that B. And as you can see, both of them, it crosses the axis here, 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 here. They're both constantly crossing the 0 axis. Hence, they're both alternating. In this instance, because we're dealing with voltage, they're both alternating voltages. So these are both alternating waveforms. Alright, so here we've got an AC waveform, and as you can see, here it starts off at 0 volts, comes all the way up to 230 volts, comes back down to minus 230 volts, back up to plus 230 volts. So this is what here in the UK, our mains power looks like. So we all have AC power, which are delivered to our homes. They enter our homes at 230 volts. And so the main takeaway here is that these are bidirectional waveforms, because as you can see, it starts off at the 0 axis here, it crosses it here, crosses it again here, and again here. And as long as, if you just keep going through time, you're going to keep seeing that these waveforms are going to constantly keep crossing the 0 axis, hence they're bidirectional waveforms. All right, so let's move on to now the characteristics of waveforms. So when you're dealing with waveforms, the key thing that you need to know is that each waveform, regardless to what it is, has 3 characteristics. It's going to have a period, it's going to have a frequency, and it's going to have an amplitude. You may have already come across these terms if you've dealt with other forms of waveforms before. It's exactly the same thing. So the periods are denoted with capital T. So whenever you see the capital T, when you're dealing with waveforms, we're talking about the period. The period is actually the time in seconds for the waveform to complete a cycle or to repeat itself. In terms of frequency is denoted with the lowercase f, and the frequency is how many times one cycle of the waveform is repeated per second. So how many cycles you're going to get in 1 second. And amplitude is denoted with a capital A. And there's a technical definition of amplitude, but the way that I'll go through it with you when we get there in a couple of minutes. But amplitude is basically the maximum value of the voltage or current, if you think of it that way, right? Amplitude is going to be the maximum value of voltage or current. But we'll go through the technical definition of it as well. All right, so for period is obviously the time in seconds to complete 1 cycle. So here I've got a waveform and I've got 1 second marked off here. If we count how many cycles it does, a cycle, in case you didn't know, is when the waveform starts, how long it takes the waveform to go all the way across, back, and to back where it started. Right? In terms of, when I say started, obviously it's moving through time. This is time, right? But how long does it take? So it goes, for example, here, comes back up to here, this 0 point, but it didn't start here because now it's going down, comes back up, and now it ends over here. So that's 1 cycle. So here, this whole time here is 1 second. So the waveform does 1 cycle, and then it does another cycle. So it does 2 cycles. So this waveform has a period of ½ a second. Why? Because we're talking about how long does it take the waveform to complete 1 cycle. And as you can see, it completes 2 cycles in 1 second. So therefore, it means that divide that by 2, we've got it completing 1 cycle every ½ a second. So this waveform, it has a period of 0.5 seconds. All right, so here we've got another waveform. So tell me, from looking at this, what's the waveform's period? So as you can see, it does 1 cycle, another cycle, another cycle. So it's doing 3 cycles. I've been a bit tricky here. The whole waveform is 3 seconds. We're only interested in the time in seconds it takes for the waveform to complete 1 cycle. Let's just look at 1 cycle here. How long does it take to complete 1 cycle? 1 second. Hence, the period of this waveform is equal to 1 second. So this waveform here takes 2 times as long as this waveform here. Even though when you're looking at both of them, it seems like the second waveform is faster than the first. But you have to remember, in terms of when we're looking at in terms of time, this one 3 seconds, this one's only 1 second. The first waveform completes the cycle every ½ a second. The second one completes the cycle every second. So it's 2 times as slow. In terms of the mains AC power in the UK, it completes a waveform every 20 milliseconds. So pretty rapid. All right, so moving on to frequency. The main thing to remember when it comes to frequency is that it's denoted with the F, the lowercase f, and it's measured in hertz, HZ. Yeah. All right, now with frequency, it can be a little bit confusing. The reason being is because remember with period, we're looking at the time in seconds it takes for the waveform to repeat itself. With frequency, we're looking at how many times one cycle of the waveform is repeated. So how many times one cycle occurs every second. How many cycles per second? How many cycles per second? Okay, so we're dealing with the unit being 1 second. So if I count for 1 second, how many times in that 1 second did the waveform oscillate? How many times did it cycle through? The difference between period is asking how long did it take the waveform to do one cycle. So a good way to think about this in terms of an example, which I like, is when you're dealing with period, you're asking, okay, how long did it take me to drive there? Right? So it took me an hour to drive home. When we're dealing with frequency, we're talking about how fast was I going driving home. So I was driving home at 70 miles per hour. It's very different. So period, took me an hour to get home. Frequency, I drove home at 70 miles per hour. We're talking more about the rate or the speed at which the waveform's going. If we look here, we've got 1 second here. We're asking how many cycles occur per second for this blue waveform. The answer is we're getting 1 cycle per second. So we have a 1 hertz frequency. Okay. Okay, so we've got another waveform here. Same question. How many cycles per second? So as you can see, we've got 1 cycle here. And we've got another cycle here. So this is the second cycle. This is the first cycle. So how many cycles in 1 second? We've got 2 cycles per second. That gives us a 2 hertz frequency. So another thing, when we're dealing with mains here in the UK, in terms of how many times we have a cycle from the AC per second, we have 50. So our mains here in the UK is 50 hertz, which means that the AC waveform oscillates 50 times every second. So that's different to what we said up here, which was it takes 20 milliseconds to complete one waveform. Right? It takes 20 milliseconds to complete one waveform, and then we've got it in 1 second completing 50 cycles. Cool. Hopefully that makes sense. You see the difference. If it's a bit hard, just think of the car analogy that took you an hour to drive home and you drove home at 70 miles per hour. All right, I've given you a bit of a tricky one here, but tell me what's this signal's frequency in hertz? So we've got 1 second here. All right. So how many cycles has it completed in 1 second? So it's completed 1 cycle here, and then it's gone up and reached its peak. Okay. So it's done 1 cycle, and its peak is it hits its peak at a quarter, like a quarter of the way there. Half of the waveform is back at 0. 2/3 or 3/4 of the way. 3/4 of the way to completing it is here, and then it completes away from here. Right. So we've got it doing 1 1/4 waveforms in 1 second. So that means that this has 1.25 hertz. It's doing 1 1/4 waveforms every second. Cool. All right, another quick one. Tell me what's the hertz for this one. So you've got a whole 1 second here, and you've got 1, 2, 3, 4 waveforms being completed. So you have a 4 hertz waveform. Hopefully I've driven that home enough. Okay, so let's move on to amplitude. So remember, amplitude is the max current or max voltage. Now I just want to touch on the official definition of amplitude as well. I'll try and explain it a bit later on though. So amplitude is the fluctuation or the displacement of a wave from its mean value. Okay, so just keep that in your pocket for one moment. We'll touch first on what amplitude is, and then I'll give you an explanation a bit more into that. We'll draw some images. All right, so here I've got a 5-volt square wave where it's basically going from 0 volts up to 5, back down to 0. So in terms of amplitude, what's the maximum value that this waveform has of voltage? It's obviously going to be the 5 volts, which occurs all here, 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 and here. So the amplitude there, 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 and there. Cool. All right, so I've got another sine wave here as well. What's the amplitude here? So max voltage, it occurs here, it occurs here, and it occurs here. So you can see it's 5 volts here, minus 5 volts here, 5 volts here. So we have an amplitude on this sine wave of 5 volts. We've got a triangle wave here, so we've got our max, our amplitudes here, here, here. So this again, likewise, has a max voltage of 5 volts, minus 5 volts. That gives us an amplitude of 5 volts. This should be the easiest one. You've just got a DC wave there, straight wave. I mean, it could be DC, it could be anything really, actually. As long as it's just a steady 5 volts. I mean, pretend that this is a straight line. I know it's not exactly straight, but yeah. You can see the amplitude here, again, 5 volts, 5 volts, 5 volts, 5 volts. Cool. All right, have a go at this one. What's the amplitude here? This is a bit more trickier, huh? Yeah. So this is where the definition, the official definition goes. Because you could say, well, what's the maximum voltage, the maximum value of voltage here? And, it works most of the time, especially when you're dealing with sine waves that go across 0. But if you're dealing with a let's say, for example, you had this wave here. It's a voltage that starts at 15 volts, goes up to 20 volts, comes back down to 10 volts over here, goes back up to 20 volts, and comes back at about around 15 volts here. This amplitude here is not 20 volts. It's not. So let's go to our official definition. Amplitude is the fluctuation or displacement of a wave from its mean value. Okay, so what's the mean value of this waveform? Well, I can tell you, I just draw a straight line straight through it. All right, so although my sine wave drawing isn't the best, the mean value here would be 15 volts. Right, line straight through the middle of both of them. Okay, so what we've said is that amplitude is the fluctuation or displacement of a wave from its mean value. So if we take the maximum voltage from its mean value, so the mean value being here, 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 what's the maximum voltage from the sine wave's mean value? Well, it's up here, 20 volts. So from 15 volts up to 20 volts is 5 volts. So you have a 5 volt amplitude here, got a 5 volt amplitude here, and 5 volt here. So this sine wave here is exactly the same as this sine wave here, with the only difference being that this one's crossing 0, whilst this one isn't. And another important point about when you're dealing with voltages or even currents for that matter is you have what are called peak to peaks. We'll touch on this more in a later video, but peak to peak basically means when you take in the voltage from this peak and this peak here. So here you've got a voltage difference, and you've got 20 volts up here and you've got 10 volts here. So the peak to peak voltage of this waveform is 10 volts. Also, you've got an amplitude of 5 volts and a peak to peak voltage of 10 volts. All right, so I just want to touch on some of the different waveform types. I've mentioned most of these in the video already anyways, but these are the 4 waveform types that you need to be comfortable with. You've got a sine wave here, right, which just goes like that. You've got a square wave that goes like that. You've got a triangle wave, and you've got a sawtooth wave. Hopefully you know why the sawtooth and the triangle are called their names. Obviously because the triangle wave is like triangles, and the sawtooth wave is like teeth on a saw. Okay, so in terms of a sine wave, the thing to remember about sine waves is that they're smooth periodic oscillations. So they're always, like that, for example, always nice and smooth. The thing with square waves is that they're always alternating between a minimum and a maximum. And ideally, I haven't drawn it the best, but ideally they do it instantly as well. That's the thing. So for example, here, at this point here, you've got 5 volts, and here you've got 0. So right here, you're at 5 volts, and then instantly you drop down to 0 volts. And you're at 0 volts, and instantly you climb back up to 5 volts. In reality, it's not really like that, but you know, the thing with square waves is that ideally they're instant rises and falls from their minimum to straight to the maximum. With triangle waves, you have you have a continuous rise and a continuous fall in voltage or current. So constantly with a triangle wave, the voltage is going from 0 and it's rising at the same rate up to its maximum, then back down to its minimum, back up to its maximum, and then back down to its minimum at a constant steady rate. And then sawtooths, they usually rise linearly upwards and then fall instantly downwards. They rise instantly, usually linearly upwards, and then instantly downwards. So they have like the characteristic in terms of rising of a triangle wave, but they drop instantly like a square wave. Cool. All right, so briefly, I just want to finalize up with, tell me in terms of frequency, in terms of amplitude, and in terms of period, how do these two waveforms relate? So do they have the same time, frequency, and amplitude? Are they different? What do you think? You've got a red waveform, we can call that waveform A, and you've got a blue waveform, waveform B. Okay, so in terms of waveform A, it starts here, and then it does one cycle at about here, and then does another cycle here. So it does 2 cycles in 1 second. So 2 cycles per second, right? And it takes about half a second to complete 1 cycle. It does 0.5 seconds per cycle. Okay, so what about waveform B? You've got 1 complete cycle here, another complete cycle here, another complete cycle here, and then a bit like it does another probably 3/4 of a cycle before it would have ended up back at 0 here, right? So it does 1, 2, 3, 3.75 cycles per second. So do they have the same frequency? Definitely not. Then how long does it take to do 1 cycle? So it's about 0.25 seconds per cycle. So definitely don't have the same time period either. Now in terms of amplitude, I didn't put anything on the axis, but it doesn't matter. You can see that they both rise and fall to the same level. So they both have the same amplitude. Cool. All right, so this might be a little bit more tricky, but hopefully you can see that these two waveforms are exactly the same. I'll show you. You see that? They're exactly the same. So what we can say here about these waveforms is that they have the same amplitude because they're at the same level, right? They're gonna have the exact same frequency because why? They complete the same amount of cycles per second, and they're gonna take exactly the same amount of time to complete 1 cycle, which is around about here, which I don't know, we could say is like 0.6 seconds. So these two waveforms are gonna have the exact same amplitude, the exact same frequency, and the exact same period. The one thing that we would say about these two waveforms, which we'll touch on later, is that these two waveforms are out of phase. Although they're exactly the same, they're not operating at the same time frame. Meaning that, the blue waveform here it starts slower than the red one. If you imagine trying to press, you had 2 buttons that you were pressing, right? And you wanted to press waveform A, waveform B. You might have pressed this waveform B, I don't know, 0.1 seconds slower than you pressed that one. So then the waveform B started later, for example. All right, and then finally, we'll end this one here. Tell me what you think about these two waveforms. So we've got a triangle waveform and a sine wave. So how do they compare in terms of amplitude? frequency, and period. So as you can see, they both do a cycle and a half every second. So that means we know that they have a frequency of 1.5. It takes them about 0.6 seconds to complete one cycle each. So they have, you know, for example, a period of 0.6 second. There's a period. Now, in terms of amplitude, how do they compare? So obviously, I haven't put anything on the x-axis. I've done that intentionally just to leave it blank. But you can see here that the blue waveform has a much larger amplitude. You can see that here versus here. Here versus here. Here versus here. The peak of the blue one is much higher than the red one. So they have the same frequency, same period, but a different amplitude. Cool. Alright guys, so I told you there wouldn't be any maths in this video, but in the next one we'll carry on with waveforms, but we'll chuck in some maths as well, so should get exciting. I'll see you guys in the next one. If you enjoyed the video, give it a like. Thanks for watching.